Here is a more complex energy problem. So if I have a ramp here with a spring attached to it, and I have a mass sitting up here, so let's just start out with assuming that this is frictionless, so mu sub k is equal to 0. The question is, how far will the spring compress if the mass just slides down? We'll start with an initial speed of 0 meters per second. How much will the spring compress? We'll let the mass be 5 kilograms. We'll let the distance from here to here be L. And the amount that this compresses, we'll just let be the value Z. Spring constant for the spring, we're going to make 20 newtons per meter. And don't know if there's other information that we'll need, but we'll get to it when we do. So if we think about the forces acting on the mass here, we have weight acting down, we have normal force acting this way. There is no friction. Eventually, with time, we're going to have one other force acting on. We'll have the force from the spring, and so we have normal force and we have weight. And if we think about the work being done, that the weight is obviously going to be doing work. It is getting closer to the surface of the Earth. The normal force, however, is not doing any work because it is perpendicular to the displacement. So the work done by the normal force equals 0 because the normal force is perpendicular to the displacement. Now, in the case of the ski slope problem, we looked at the instantaneous displacement. Normal force is perpendicular to it. But in this particular case, it's a constant slope, and so it's much easier to see that my displacement will be down the ramp, and my normal force will be perpendicular to the ramp. And so therefore, work, which is a dot product, work is force dot displacement, equals 0. One other bit of information we need is this angle right here. And so let this be about 37 degrees. Ultimately, I want the sine of theta to be 0.6 and the cosine of theta to be 0.8. So now that we've established that there is no work being done by the non-conservative force because weight and the spring force, this is an ideal elastic medium right here. And so those are both conservative forces, therefore energy is conserved. So we just start out with energy initial equals energy final. Now my energies, I have kinetic plus potential, and I have two types of potential because I have two conservative forces, therefore I have two potential energy formulas. So Ki plus, there's the gravitational potential energy associated with weight, and then there's the spring potential energy or elastic potential energy associated with the spring force or the elastic force from the spring. Again, I'm using a subscript S here instead of an E because I reserve E for electric. So I'm using S for spring. And so that should be equal to the total final. Now we do the formulas. I got 1/2 mv initial squared plus mgh initial plus 1/2 k delta x initial squared equals, and I do want to point out that this K right here is the spring constant. It is not the kinetic energy. Kinetic energy is a capital K, and the spring constant is a lowercase k. And also, since this is usually a point early in the course, before we really get to talking about harmonic motion, the spring constant is really a stiffness constant. And so, and then carrying on, basically the same formulas except for final. Now we get rid of things. Now, in the problem, I said that it starts out at a speed of 0. Starts at a speed of 0, so that is 0 because the initial speed is 0. The spring just starts out sort of in its natural position, so delta x initial is equal to 0. That's 0 meters, and this is 0 meters per second. The final speed is also going to be 0. That's implied by the problem, the fact that we're getting to that spring at the greatest compression, and when it's compressed the most, the object's not moving. It's a turnaround point, so that's a 0 also. And we can get rid of one other. So it all depends on where we want to consider the height to be 0. So if we come back up here, and let's just put the height of 0 at, let's see, that's the farthest that it goes. So we'll make height is equal to 0 right there. Now, other logical choices to make height is 0. One of them is to put it right here. The height is equal to 0 at the beginning, in which case the final height would be negative. And also I tend to, even though I'm not doing it in this particular video, I tend to do it right at that point as well. but I'm not doing that in this particular case. And so making height is equal to 0 at the bottom. That is 0 because H final is equal to 0 because I say so. And so our problem has now been reduced. Again, this is a frictionless problem. Energy is conserved. There's my total potential energy at the beginning and then my total final energy at the end. So we start out with all gravitational potential energy. As it falls, as it goes down the ramp, that gravitational potential energy gets transferred into some kinetic energy along the way. At some point, the kinetic energy will stop increasing, but once you hit the spring, some of this energy from, well, in essence, I'd say gravitational potential is being transferred, some into kinetic and some into the elastic potential. And then at some point, the kinetic and the gravitational potential both start giving in some of its energy units into the elastic potential. So it's a whole matter of transfer because the conservative forces are doing work. We have energy being transferred from one form to another, as opposed to from one object to another. And we end up with here. So all the kinetic energy that was gained is eventually given away. And ultimately, we're trying to find out how much it compressed, and so that we're looking for that number right there. Let's plug in what we know. So the object's at a slant right here. I know that the mass is going to be moving a distance of L plus Z. So my initial height, if that angle there is theta, would be L plus Z times the sine of theta. And so my initial potential energy is mg times my height, which is L plus Z sine of theta. And that's going to be equal to 1/2 k times z squared, since z is how much the spring actually compresses. Now we do a little distributing here, so I have mgl sine theta plus mgz sine theta is equal to 1/2 kz squared. I have my unknown right here. I do have a squared term, and so we are dealing with a quadratic. So I am dealing with a quadratic here, so I need to set this equal to 0 so I can use the formula. So I have 0 is equal to 1/2 kz squared. I am putting everything over on the right-hand side because it's my own personal eccentricity. I'd like the quadratic term to have a positive coefficient. So I'm going to be minus mg sine theta, z minus mgl sine theta. Now, there might be some advantage to actually plugging into the quadratic formula using the variables, but I'm going to stick in numbers at this point. So we have 0 is equal to 10 z squared, since k is equal to 20. M is 5. Theta, or sine of theta, more specifically, is 0.6. G, let's go ahead and put this on a planet where g is equal to 10 meters per second squared. So not Earth. And so we end up with minus, so that's 50 times 0.6, so that's 30z. And then the last thing over here is we have mg is 50 times L is 150 times 0.6 is 90. So minus 90. Now that just so happens that they all are divisible by 10, so I'm going to simplify here. So 0 is equal to z squared minus 3z minus 9. So we have relatively simple numbers here. So z is equal to 3 plus or minus the square root of 3 squared minus 4 times 1 times negative 9 over 2 times 1. And so this becomes 3 plus or minus the square root of 45 divided by 2. Two solutions here. It is a quadratic, so one of our solutions is 4.854 meters, and the other solution is negative 1.854 meters. Now, it's the positive solution that makes a difference here. I had z being a positive number. If we flash back up to the top, z is how far the spring is compressed. Now, that negative number would involve compression going in this direction. Well, I guess not compression. It would involve an extension going in the other direction. Because, again, we're just looking for spots where the energy is the same. And I'm not claiming that when the mass gets to this point right here, as it's going on the way down, that the spring is stretched in any way. However, it is going to show up again in a slightly different problem. But that is how far the spring compresses. So now we have, again, our same angle 37 degrees. We have a spring that has been compressed and the mass sitting on it right here. And so that distance right there was 4.854 meters. And it originally started up here. Now, if the spring then released and started extending, it would push the mass back to its original starting point. So that is how far up it would go. However, let's change the problem slightly. So if the mass sticks to the spring, how far up the ramp will the mass go? And so now what we're going for is this thing is going to extend up to there, where this is the equilibrium spot right here, and the mass is still attached to the spring. This is angle theta, same details as before. Again, on some strange planet where g is equal to 10 meters per second squared. Again, energy is conserved. All of that still stays the same. We end up with 1/2 mv initial squared plus mgh initial plus 1/2 k delta x initial squared equals 1/2 mv final squared plus mgh final plus 1/2 k delta x final squared. This is my initial situation right here, and this is final. So again, we first have to see what we can get rid of, and for the exact same reason as before, initially it's at 0. This is at maximum compression. My initial speed is 0. My final speed also is 0 because I'm looking to see how far up it will go. So final speed is equal to 0, and these are of course meters per second. My stretching of the spring neither of them are 0. I'm going to go ahead and make this z. And we figure out where the initial height is 0. And I'm going to pick the same spot down here. So let's make height is equal to 0 at that point. So that is 0 because I say so. And so our equation comes down to 1/2 times the spring constant times the initial, how far off the spring is from equilibrium, is equal to mgh final plus 1/2 k delta x final squared. This is what we're actually trying to find. So now let's plug in some numbers here. I know that k is equal to 20 newtons per meter. My initial position right here, the initial amounts that the spring is off of equilibrium, or in this particular case, it's compression. It was 4.854 meters. Mass is 5, g is 10. That's 5 kilograms and 10 meters per second squared. HF is going to be 4.854 plus z. That is the distance up the ramp. This is the 4.854 meters. However, we want the vertical distance, so times the sine of theta, and this is 0.6. K is 20, and delta XF is z. That's delta XF is z. That is what we're trying to find. So plugging in, on the left-hand side, we get 235.623 joules. That's going to be equal to, we'll end up with 50 times 0.6, which is 30. And then we're going to distribute that 30 times the 4.854, so and get 145.623 plus 30z. That is my gravitational potential energy. Looking at that again, that's mgHf. So we basically had mg times the hypotenuse of that triangle there, the 4.854 plus z, times the sine of theta to get the vertical height. And to multiply all that out, you get this, plus 10z squared. And again, we're trying to find z here. So we end up with 0 is equal to 10z squared plus 30z plus, and then we're subtracting this from both sides, and we get negative 90. So very similar to what we had before, except we have a plus sign here, and as before we had a negative sign. Again, we have coefficients that are all divisible by 10, so I have 0 is equal to z squared plus 3z minus 90. And if you plug into the quadratic formula, you get z is equal to negative 3 plus or minus the square root of 45 divided by 2. And I got 45 because we just did that problem. And we get 1.854 meters and negative 4.854 meters. And so this is that, we had that negative answer before, but this is where with the mass attached, how far the spring stretches in order for the box to basically have the same energy as it had before. Well, actually, at maximum extension, that's the point when it stops. If we scroll back up and we look at the energies, initially, our initial energy, K initial was 0, UG initial was MGH, so 5 times 10 times how far up from 0, which was 7.854, times the sine of 37 degrees, which was 0.6, and we have 235.623 joules. That is the amount of energy we had at the beginning of the problem, and as we discovered down here, that is the amount of energy we had when the spring was at the bottom, or the mass was at, that's the amount of energy we had when the spring was at the bottom. And if we look at this new spot up here, so my energy final at the end of the second problem, K final plus UG final plus US final. This was 0 because it was stopped, plus mg, which is 50, times the height, which was, well, it was 4.854, and then it went up 1.854, 6.708, times the sine of 37 degrees, plus my spring here, which is 1/2 times 20 times 1.854 squared. Again, this number right here comes from the fact that it started out down at the bottom of the spring. The picture started at the bottom of the spring. It went up 4.854 plus this amount Z. And cranking that out, 201.246 joules plus 34.373 joules. And if you add those together, we get 235.62 joules. So very close to the first one. I rounded up, it was 619 in my calculations, but rounded off to make it look better. So this amount of energy we had at the end, and the discrepancy of 0.03 of a joule comes from rounding. So let's take a look at the same problem, except this time we're going to throw in friction. So I have spring here sitting in its natural position, and then I have a mass sitting up here. This angle is theta. This is some mass n, which we're going to make 5 kilograms. Spring constant, we're going to make 20 newtons per meter. Put on some strange planet where g is equal to 10 meters per second squared. Theta, we're going to make it such that the sine of theta is 0.6 and the cosine of theta is 0.8, which puts us at roughly 37 degrees. It's going to slide 3 meters before it gets to the spring, at which point it's going to start compressing the spring. We're going to make the initial speed 0 meters per second. It's going to start at rest, and we're going to make mu sub k equal to 0.2. We do need to take a look at the forces acting on it. So if we look at the forces, so if weight acting down, we have normal force acting up to the left. We're going to have friction acting this way. Ultimately, we're going to have a spring force also. If we think about conservative and non-conservative forces, we have our conservative forces here, and we have our non-conservative forces here. As before, normal force is not doing any work whatsoever, but friction is. Friction, this is kinetic friction, is doing some work. So we need to figure that out, but friction is dependent on the normal force. So I do need to break this up to figure out what the normal force is. I know acceleration down is going to be down the ramp, and therefore there's no acceleration perpendicular to the ramp. So I'm breaking weight up, as we have done in many times. So we have W cosine theta, W sine theta, normal force, friction, and at some point we have the force from the spring. Bottom line is the normal force, magnitude of the normal force is going to be equal to W cosine of theta. As we do that, we end up with our kinetic friction, which is mu k times y. It's mu k W cosine theta. We can actually come out with a number here. This is 0.2 times 50 times 0.8, which ends up being 8 newtons. We have non-conservative work is equal to the change in energy. Our non-conservative work is the friction times the displacement. And for displacement this time, I'm not going to use x because I use x elsewhere as well. And so we're going to do delta S, and that's going to be equal to E final minus E initial. I do want to point out that it's going to compress a certain amount. That's what we're trying to find here. So let's make that Z. That's going to be the delta X in terms of the spring. And so E initial plus this. Now the displacement of the box is down the ramp, so that is going to be delta S. The friction is up the ramp. We have 180 degrees between them, and so this becomes negative friction delta S is equal to E final. We have our initial kinetic plus our initial potentials, or minus our friction delta S is equal to K final plus UG final plus US final. Now we get rid of stuff. I know this is 0 because the initial speed is 0. This is 0 because my final speed is 0. We're looking at maximum compression. My initial spring is 0 because delta X for the spring is 0. And we are now left with, where do we want to make H is equal to 0? And let's, like we did before, let's make H is equal to 0 at maximum compression. So at maximum compression, the box would be here. And so that is where we're going to make H equals 0. And so this is 0 because I say so. So I'm left with mgh initial minus F delta S is equal to 1/2 K delta X squared. So I have mg. Now my hypotenuse here is going to be 3 plus z. So this is 3 plus z times the sine of theta, minus my friction, which is 8, as we have done, times how far it slides, which is 3 plus z, is equal to 1/2 K z squared. Doing some distributing and some math. So that's 30 times 3, so that's 90, plus 30z, minus 24 minus 8z is equal to, that whole thing there is 10, so 10z squared. Getting everything over onto one side, I have 0 is equal to 10z squared, and then bringing, that's 22z, so bring it over, minus 22z, and then combining those, we get 66 on the left-hand side, plus negative 66 on the right-hand side. Could divide by 2 to simplify it, but it doesn't really benefit us a whole lot from my point of view, but feel free to divide everything by 2 if you wish. But if you don't divide by 2, you get z is equal to 22 plus or minus the square root of 22 squared minus 4 times 10 times negative 66, all divided by 2 times 10. So the discriminant in this particular case is 3124. And so take the square root. So I get 22 plus or minus 55.893 divided by 20. And I get negative 1.6946, or 3.895 meters. These are meters. This is the one that makes sense. Now, again, going back to the problem here, we have a ramp, we have a box sitting on it, we have the spring. When the spring is compressed, 3.895 meters, that it will come to rest. That's maximum compression. If we look at the negative value there, the negative 1.6946, that is not the point in which, if it sticks to the spring, it's going to get, that's where it's going to bounce back to, unlike without friction, because with friction, it's going to be losing energy as it's bouncing back. And so that is more than I would expect it to actually go. And so we could look at that, and we would set it up, so K initial, which is now down here, plus U initial, G, plus US initial, minus friction times the displacement going back up the ramp, is equal to K final plus UG final plus US final. So this is, if the mass attaches to the spring, that's still going to be 0, that's going to be 0. Since this is my initial right here, and my final is when it is now extended, we're going to make that 0. And we end up with 1/2 k times 3.8946 squared minus my friction, which is 8 times how far it goes back up, which is going to be 3.8946 plus z. Let's go ahead and establish that it's going to spring back up a distance z, equals my final, which is mg times 3.8946 plus z times the sine of theta plus 1/2 k z squared. Again, we're dealing with a quadratic, and this is 151.68 joules minus 31.157 minus 8z is equal to, that combined is 30, 116.838 plus 30z plus 10z squared. And now let's get all that stuff together. So I have 0 is equal to 10z squared, adding that over to the other side, plus 38z. And then I now have minus 3.685. And so z equals negative 38 plus or minus the square root of 38 squared minus 3.685 times 4 times 10. Slightly different order than is traditional. That should be a negative there, over 20. And so I get negative 38 plus or minus 39.89 divided by 20. And I do have two answers again, but only the positive one is going to make sense. And I get 0.0946 meters. It just barely gets past equilibrium. And then negative 3.4945. And so the fact that the magnitude of that is less than how far it had stretched before, which was 3.895, it's an indication of energy that was lost. Anyway, that is how far it would bounce up if the mass attached to the spring with friction involved.